Okay, so in the afternoon, we end off this easy lemma. So maybe we just recall the statement of it. It just says that if we have three condition, these three condition for one is the non-degeneracy condition. So it's gamma large equal to alpha plus beta. And another is an initial condition. So means that A1 larger than beta AZ. And regressive inequality. So AN plus 2 plus alpha beta AN large equal to gamma AN plus 1. If once you have these three inequality, then you can get a lower bound of some limit. The limit is looks very like the definition of dynamical degree. So it's the limit inf of an 1 over n. And we show that the limit inf is large equal to alpha. I think that's it's a very easy lemma, but I think it's very useful in our proofs. Okay, now we can show how to use it. Um, so by our inequality, this two star inequality, it implies implies this inequality. So it's the first degree of Fp 2 plus Nm plus mu1 eta 2m delta m degree 1 Fp_Nm large equal to mu1 eta m epsilon m degree Fp 1 plus Nm. Okay, and now we define this degree 1 Fp_Nm to be an. So then we get a recursive inequality in this on this sequence an. We get this recursive inequality, and now we want to apply the easy lemma. So we set this alpha, beta, and gamma. Here we just ask alpha to be mu1 eta m times epsilon 2m. Beta is mu1 eta m delta m epsilon minus 2m. And gamma is mu1 eta m epsilon m. So here we pick some epsilon, which is strictly less than 1, but very close to 1. And we pick this m sufficiently enough, sufficiently large. Then we will have this mu1 eta m strictly larger than alpha and strictly larger than beta, and gamma strictly larger than alpha plus beta. So these things give you this non-degeneracy condition. And now you look at A1 divided by AZ. So what you get is degree 1 Fp over degree 1 Fp Z. Okay, so it's degree 1 Fpm over degree 1 Fpz. So it equal to degree 1 Fpm because degree 1 Fpz is just 1. And then if we take the limit, this limit of degree 1 f eta m 1 over m, by definition, it is the dynamical degree. So it's lambda 1 eta. And it is also mu1 eta. And it is strictly larger than beta 1 over m. So now if we pick M sufficiently large, uh, then this degree 1 f eta m is larger than beta. And uh, and because we know that this such degree is constant in some Zariski open subset. So we can pick some non-empty Zariski open subset U epsilon such that for every p in this U epsilon, degree 1 fpm, it is equal to A1 over AZ, and this one is strictly larger than beta. So if you pick this P contained in this uh, open subset U epsilon, then you may ask and you pick M sufficiently large, then you may ask the initial condition hold. So now you apply this easy lemma because you already have this three condition. Then it implies that for every p contained in this U epsilon, you have a lower bound of the limit inf. So it's lambda 1 and an 1 over n. And this one is large equal to alpha. And by definition, alpha is mu 1 eta m epsilon 2m. And we take the m's root, we get lambda 1 fp large equal to mu 1 eta epsilon square for every p in U epsilon. Okay, now we take epsilon tends to 1. We get the inequality we need. So it limit inf lambda 1 fp, p tends to eta, large equal to mu 1 eta, which equal to lambda 1 eta. And this is what we need. So, so this proves the lower semi-continuity for the here is for the first dynamical degree. I think for higher dynamical degree, the strategy is very similar. It's something like you want to construct some, you construct some um, higher codimensional, you construct some regressive inequality for some higher codimensional cycles, and then you try to apply this easy lemma and check all these three conditions, and you use this one to get the lower bound of the dynamical degree, and you show that in the end this you can make the lower bound tend to the upper bound, and then you get this limit. Okay, and so now I want to give an application of this another application of this regressive inequality. In fact, it's a more geometric application. Then I think it's interesting because it seems that we want to really use this complexity theory to understand our dynamical system. So this is our theorem C. So the statement is that if our F, this rational self-map F is cohomologically hyperbolic, so which means that for all these Lyapunov cohomological Lyapunov exponent is either strictly larger than 1 or strictly less than 1. So no mu I equal to 1. Then under this condition, the set of periodic points of X is Zariski dense. Okay. And I think there are many previous results for this theorem. There Brian Duval, Dean Sibony, Gage, Dean Le Guillen Tong, and many people. and also Hushovsky, Fakhodin, and me. So we get some special cases of this theorem. So I think for the first line, all by analytic method, and the last line is by algebraic method. And I think they have the algebraic and the analytic method, they have different the advantage. So the advantage of the analytic method is that once you can prove such result using analytic method, what you get is not only the Zariski density, you basically understand the distribution of the periodic points in Euclidean topology. So usually they get some equidistribution result. And the advantage of the algebraic method is that uh, it works not only over C, it works over any field. So, for example, it works even in positive characteristic. Okay, but all these previous results are for cohomological hyperbolic uh, maps. So, so now I want to give a non-cohomological hyperbolic example. So the example is very simple. You take two maps. The first map is G from P1 to P1, and the map is it maps Z to Z square. So it's a power map. No, it's a square map. And this the second map is H alpha. It depends on one parameter alpha in C star, and the map is Z mapped to alpha Z. So now you do the product of G and H alpha, you get F alpha. So it's a family of self map. It's a family of endomorphism uh, from uh, from P1 times P1 to itself. Okay. So our X is just this P1 times P1. So very easy to see that the dynamical degree of F alpha is 1 to 2. So the zero, lambda zero is 1, lambda 1 is 2, and lambda 2 is 2. So it is not cohomologically hyperbolic because lambda 1 equal to lambda 2. So the maximum value is not unique. Okay. And and uh, so easy to check that in this case, the periodic points of F alpha uh, is Zariski dense if and only if alpha is root of unity. So so I think this example shows that in the if this F is not cohomologically hyperbolic, usually whether it has Zariski dense orbit or not is very sensitive because you see that here is in one family in this family in a continuous family you have many parameters such that the periodic point is Zariski dense, but also many parameters such that the periodic point is not Zariski dense. Uh, but I think this is not a surprise because I think even in differential dynamical system, uh, we cannot expect to prove prove some very good result for all dynamical systems. We usually have some need some condition on some hyperbolicity condition, and and we think something like the hyperbolic system is something quite robust. But for non-hyperbolic things, it should be something not that stable. So this problem, the Zariski density of periodic point, I think this is not that not that it's quite quite sensitive for non-cohomologically hyperbolic maps. Okay. So now we give the proof of. In fact, it's a sketch of the proof for this theorem C. And our proof is divided by 3 steps. And this proof is in fact strongly inspired by the argument of Hrushevsky and Fakhudin for endomorphism of for amplified endomorphism of projectives and projective varieties. Okay, so our first step is to show that most of the periodic points are isolated. So under the cohomologically hyperbolic, in the cohomologically hyperbolic case, most of the periodic points are isolated. So we have the following proposition. So if f is cohomologically hyperbolic, then there is a non-empty Zariski open subset U such that for every periodic point x, if the whole orbit of x is contained in U, then x is isolated in the set fixed Fr, where R is the period of x. So we see that this the set fixed point of Fr, it is some Zariski closed subset in X, and it may have many components. So some components are of dimension large or equal to 1, and some irreducible components are just some point, so it's zero dimensional. And this proposition just say that we have a Zariski open subset such that if you have some R periodic point whose whole period is contained in U, then this component is irreducible. This component is of zero dimension. Okay, so now we give the proof. So for the simplicity, we assume that x is projective, and our map f from x to x is an endomorphism. So it's not rational. It's an endomorphism everywhere well defined. So if f is cohomologically hyperbolic, then there is a unique I such that mu I is strictly larger than 1 and mu I plus 1 is strictly less than 1. Now we fix some ample line bundle L on X, and as before, we define this Ln to be the pullback by Fn of L. And so if F is a rational map, then this Ln is indeed defined on some higher model above X. But here we assume this F is an endomorphism. So this Ln is a line bundle. It's still an ample line bundle on X. Okay. Now we pick epsilon in this interval. It's larger than the maximum value of mu I plus 1 and mu I minus 1. So you see here this mu I plus 1 is strictly less than 1. And mu I is strictly larger than 1. So mu I minus 1 is also less than 1. So and 1. So this interval is not empty. Indeed, you can think this epsilon is something very close to 1. It's strictly larger than 1, but very close to 1. And now we pick this m sufficiently large. Then you have the following inequality. So 1 plus mu I m, mu I plus 1 m strictly less than epsilon m mu I m. Okay, now we apply this recursive inequality. Apply our recursive inequality. We get this line bundle. MM equal to L2M plus mu I m mu I plus 1 m L minus epsilon m mu I m L m, and it is big. Now we define B to be the stable base locus of this MM. So it's the intersection of BS and uh, the base locus of the linear system N MM. And so because MM is big, so this B is a proper closed subset of X. So we define U to be the complement of this B. So it's X minus B. So it's a non-empty Zariski open subset. Now, if you have some periodic point X whose whole orbit is contained in U, uh, and by contradiction, we assume that this point is not isolated in this fixed FR, where R is the period of X. Because it is not isolated, so you can pick a curve in this fixed FR which contains X. Okay, so you see that every point in C uh, is a R periodic point. So you look at the set, the Fn push forward C for all n larger equal to Z. This is indeed a finite set. This is indeed a finite set. Okay, because it's a finite set, so you have some n. Uh, you have some positive n, such that this intersection number f m n plus 1 push forward c times l take maximum value. Because it's a finite subset, so you can always take one element to make this intersection to be maximum. So as the orbit of X is contained in U, so this FMNC contains a point in U. So the intersection of FMNC and U is not empty. Okay, so it means that this FMNC is not contained in the base locus of this this MM. Then one can show that this MM intersect this FMN star C is larger equal to Z. Okay, now we apply the projection formula. Apply the projection formula, we get the following. So this we first have this mm, yes. Okay. Yes. Here we just use this formula star star, and we write this to be the combination of some pullback of L, and then we apply this projection formula to we replace this push forward of C to be some to get some pullback of L. Then we get the following inequality. So it's L n plus 2m intersect C plus mu I m mu I plus 1m L nm times c large or equal to epsilon m mu I m L n plus 1m times c. Okay, but by our choice, the intersection number in the right hand side, this L n plus 1m times c, it is maximum. The right hand side is maximum. So if you the divide by the right hand side, you can get uh, 1 plus mu I m mu I plus 1 m large equal to epsilon m mu I m. And this is a contradiction. This is contradiction to our assumption star. Because in fact you can see it. Um, because this point is that this mu I plus 1 is strictly less than 1. And here this epsilon is strictly less than 1 but very close to 1. So the right hand side is basically mu I m. So it has larger order. Okay, this is the first step. So we just recall that in the first step we show that almost basically almost all periodic points are isolated. And the second step is indeed a theorem of Hrushevsky, Fakhdin, and Pullen. Uh, what they show is that if F is a dominant rational self-map on X defined over some finite field, then there is a Zariski open subset, non-empty Zariski so open subset. Uh, okay, then for every non-empty Zariski open subset U of X, there exists a periodic point of F whose whole orbit is contained in U. Okay, so I think their original argument just do it for endomorphisms, but if you look at it very carefully, you can see that their argument still works for rational self-map. And so indeed, it implies that if F is a dominant rational self-map over a finite field, then periodic points are Zariski dense. So without any condition, so it's always Zariski dense. And in particular, it implies our theorem 3 for the when our field K is FP bar. The key of the proof is Hrushevsky's twisted Langmuir estimate and a trick using Frobenius. Okay, so the step 3 is some more P argument. So idea is something like you first construct some periodic point in the special fiber, and you try to show that most of the periodic point in the special fiber can be lifted to a periodic point in the generic fiber. And if you have a lot of periodic point which can be lifted, then you get a lot of periodic point in the generic fiber, and then this implies the Zariski density. For the simplicity, we assume our X is just the projective space, and our field is Q. So F is some rational self-map from PD to PD defined over Q, and it is cohomologically hyperbolic. So now we apply our lower semi-continuity. So we apply our theorem B. It shows that for prime P sufficiently large, if we consider the specialization, the FP, F modular P. Then you get a map from FPD to FPD. And this is still cohomologically hyperbolic because uh, uh, because our theorem B say that the dynamical degrees are lower semi-continuous in for the Jersey topology. So it is continuous at the generic point. And you see this cohomologically hyperbolic condition, it is given by some strict inequality. So it's some open condition. So so if this dynamical degree is continuous in at the generic point, then it says that for P sufficiently large, it is still cohomologically hyperbolic. Now you apply our step two, to this specialization. It basically shows that the set of periodic points of FP is Zariski dense. And now we apply our step one. It shows that most of this periodic point we get in this step is isolated. So it shows that there are a lot of isolated periodic points in the spatial fiber. In the end, we use a dimension counting argument introduced by Fakudin and Pullen. They show that for every isolated periodic point x in the spatial fiber, every isolated periodic point in the spatial fiber can be lifted to a periodic point in the generic fiber, and this concludes the proof. Okay, maybe I can explain a bit how to do this dimension counting argument. It is quite easy. So you just look at the localization at this. You just look at the localization at this prime key. So you think your f is a your f is the map defined over z, but now you want to take advantage of the dimension of z. So basically, you add one dimension. You add one dimension, and now you consider the fixed point for this scheme map, and the fixed point can be think as the intersection of the graph and the diagonal. So if you do not add this one dimension in the base, then the intersection is zero dimensional. But now you think spec Z has one dimension. So in this case, in the total space, the intersection is of dimension at least one. You just count the dimension and you show that this dimension is at least one. And so every irreducible component of this intersection is either horizontal or vertical. But if it has a vertical component, it means that every point in this vertical component is not an isolated periodic point. So if you have some isolated periodic point in the spatial fiber, then the irreducible component passing through this point, it is always horizontal. So if you have a horizontal, irreducible component passing through this point, it means that you can lift this point to generic fiber. That's the argument. Okay. So now we just finished the proof of Zariski density of periodic points for cohomologically hyperbolic maps. Okay. So next, I want to because before we have already discussed the entropy. So entropy is the topological um, complexity, and then the dynamical degree is the algebraic complexity, and then we want to talk some arithmetic complexity. So it's the arithmetic degree. Uh, so if you um, want to study some arithmetic property, usually uh, you want everything defined over some number field or at least some finitely generated field. Okay. But here we just for the simplicity we just consider uh, the number field case. So let X be a projective variety defined over Q bar. And F from X to X is a dominant rational self-map. And we define this XF to be the set of X whose orbit is well defined, which means that for every iterator Fnx, it is not contained in the indeterminacy locus of F. Okay. Uh, Now we fix L an ample line bundle. And we fix V hat HL. So because V hat for a V hat you can always plus some O1. So for the simplicity, we can always add some positive number for this HL to assume that HL is always large equal to 1. Okay, so the arithmetic degree was introduced by Kawaguchi and Silverman. Uh, the definition is as follows. So for every point x in this xf q bar, so it is a q bar point whose orbit is well defined. Uh, so they define this upper arithmetic degree to be the Nimi soup of the height of Fnx, but you take 1 over n. And the lower arithmetic degree to be the Nimi info of HL Fnx 1 over n. Okay, and so for this arithmetic degree, the most important conjecture is the following. So we call it the Kawaguchi-Silverman conjecture. This conjecture has two parts. The first part is that they say that this arithmetic degree is well defined, which means that the upper and the lower arithmetic degree are the same. So once you can show the upper and the lower arithmetic degree are the same, then you just write alpha fx for this arithmetic degree and say that the arithmetic degree is well defined. And the second part is in the second part, it says that if the orbit of x is Zariski dense, then the arithmetic degree equal to the first dynamical degree. Okay, so I think this conjecture is very interesting because a priori this arithmetic degree, in the definition of the arithmetic degree, you use a hat. So it's some arithmetic invariant. But if this Kawaguchi-Silverman conjecture is true, it just means that this arithmetic degree is indeed not arithmetic. It's indeed an algebraic invariant. It's just a lambda 1f. So if the orbit is Zariski dense, it is lambda 1f. But even if the orbit of x is not Zariski dense, then basically you can replace x by the Zariski closure of this orbit. and then you can still get some restriction of f on this Zariski closure, and you can also get some first dynamical degree, and you apply this Kawaguchi-Silverman conjecture for this closure, you can still get this R alpha fx equal to the lambda 1 of the restriction of f on this Zariski closure. So it's still an algebraic, it's, it's still an algebraic invariant. Okay. Okay, so here I didn't define what is the weight height. I think most of you know the definition of weight height, but maybe someone do not know. So maybe I just explain what is the weight height. I think the most simple way to explain what is weight height is like this. So if you have a point x, then you can write down it. You write down x in its coordinate. And what is the weight height? The weight height is the 10. The 10 you write down this coordinate of x. So basically it means it measures the complicity of this the arithmetic complicity of this point. Okay, and a very important property is the nose-coat property. The nose-coat property is it says that basically in one number field, if you bound the height, then you have only finitely many points, and you can understand it like this. So if you have infinitely many time, then you can write down all points. But if you bound the height, then it bound the 10. You can write this number. So you can only write finitely many points. So you have only finitely many points. Have height bounded by this given number. So this is the nose-coat property. Okay, so what's the arithmetic degree? The arithmetic degree is something like you need to consider the dynamical system. So usually, if you have a point x, and if you iterate this point, then usually it become more and more complicated. It become more and more complicated, and the arithmetic degree measures how fast it become complicated. So okay, so it's like this. So here I give some known result for this Kawaguchi-Silverman conjecture. Uh, I divided it into some classes. I think the first classes is uh, I think is some basic case. So for example, F is some polarized endomorphism, or some endomorphism of abelian variety, endomorphism of semi-abelian variety, something like this. So I think all these things are for some very the argument are not that complicated, and for some quite concrete. Uh, you can do it in some quite concrete way. And I think basically all these cases are already contained in the paper where Kawaguchi and Silverman they define this arithmetic degree. This is the basic case. And so this is the Zedel family. And first family, I think this is given by the work of many people. So for example, Kawaguchi and Masuzawa, Sano, Shibata, and Meng Shen and Zhang Deqi. So for example, I think one very clean statement is if f is an endomorphism of a projective surface, then the Kawaguchi-Silverman conjecture is true. And they also get many other cases. And I think all these cases, the surface case and some other cases are all by this way. So you need to do this minimum model program and try to reduce this F to the basic case. So you try to reduce this dynamical system to some polarized endomorphism, some endomorphism of abelian variety, and something like this. So yes, here you have quite a lot work. I think mm, I think this basically this method uh, uh, at the moment, what I know is that this method basically it's quite useful for endomorphism, but for rational self-map, I think a rational self-map is quite hard to use this kind of argument because for rational self-map you can uh, I think basically you cannot reduce usually you cannot reduce it to polarized endomorphism or endomorphism of abelian variety. Okay. And I think there is also an important work is given by Kawaguchi and Silverman. So they prove the existence path. So for endomorphism of projective variety. So you see that in the Kawaguchi-Silverman conjecture, there are two parts. The first part is the existence of arithmetic degree. I think this is still quite difficult in the rational self-map case, but for endomorphism, it was already proved by Kawaguchi and Silverman. Okay, so recently there are many progress on this Kawaguchi-Silverman conjecture, and all these progress are based on this recursive inequality we mentioned before. I think one significant result is this one for Masuda. I think it's first proved by Masuzawa and Wang Long in some special case and by Masuzawa in some more general case. So it says that if the orbit of X is generic, here generic means that in the Zariski topology, this Fnx tends to the generic point. So in other words, it means that the orbit of X for every for every proper subvariety, this orbit of X only meet it finitely many times. So if you assume that the the orbit is generic, then the arithmetic degree is well defined. So it means that the upper and the lower arithmetic degree are the same. Moreover, they should not only show that it's well defined, it shows that its value is contained in this finite set. So it's in the set of Neapol of exponent. So it's mu1 to mu dimension x. Okay. So so we can see that in Kawaguchi-Silverman conjecture, the condition is something like the orbit of X is Zariski dense. And here, the condition is something like the Fnx is generic. So what's the relation between this condition? It's like this. So first, if Fnx is generic, of course its orbit is Zariski dense. But uh, but if you can still get this inverse direction if you assume the dynamical model Lang conjecture. So the dynamical model Lang conjecture say that if the orbit of X is Zariski dense, then this sequence is indeed generic. Okay, so if you assume this dynamical model Lang conjecture, then then this result of Masuzawa and Masuzawa 1 uh, directly implies this Kawaguchi-Silverman conjecture if the first dynamical degree is strictly larger than the second dynamical degree. So it's lambda 1 strictly larger than lambda 2. So because if lambda 1 strictly larger than lambda 2, it means that this mu1 is strictly larger than 1, but all this mu2, mu3, all other cohomological degree is strictly less than 1. But by the definition, the arithmetic degree is always larger or equal to 1. So it can only take value lambda 1. So you get this Kawaguchi-Silverman conjecture. So here you remember this mu1 and lambda 1 are the same. Okay, so here you need to assume this dynamical model conjecture. And if you want to get an unconditional result, um, so I have an unconditional result is if you assume the dimension of x is equal to 2, and lambda 1 strictly larger than lambda 2, then even we do not know the dynamical model conjecture, in this case, we can still prove this Kawaguchi-Silverman conjecture unconditionally. Okay, so for the Kawaguchi-Silverman conjecture, there are not so many general results. But if I want to give one general result, I think is this one. So it was first proved by Kawaguchi and Silverman in the endomorphism case, and Matsuzawa for the rational self-map case. The statement is for every x in this XF Q bar. So the Kawaguchi-Silverman conjecture say that the arithmetic degree equal to the dynamical degree. But here the theorem is that the upper bound is okay. So it's the upper arithmetic degree is less equal to the first dynamical degree. So this part is true. I think the original proof of this of Matsuzawa is by some quite a complicated computation, and here I want to give I will give some simpler proof, but I think I do not have time to give this proof. I do not have time to give this proof in this lecture, so I will do it in next lecture. But maybe I can just say the idea. So the idea is something like so if you want to have such inequality, you need to get some inequality, some height inequality, and here our argument is that we want to find two height inequality. One height inequality is quite weak, but it works everywhere. And we want to also construct another stronger inequality. But the stronger inequality is it does not work everywhere. It only works on some open subset. So then we want to combine these two inequality. It's something like you look at the orbit of x. If it is contained in some bad locus, then you use this weaker inequality. And if it contains not contains in the bad locus, then you apply this stronger inequality. And you want to show that most of the time you are not in the bad locus, then you combine them, and then you get the good, some quite good upper bound, and taking limit, you get what you want. So I think you can think it like this. So for example, if you are a student, then and you want to take some exam, and there are some questions which you know how to do, and there are also some questions you do not know how to do. So now I think the strategy is that if for some question you know how to do, then you do it very carefully, so you get a good bound. But for the questions you do not know how to do, but it is you have only A, B, C, D four choice, so you just choose one randomly, so you get some trivial bound is something like one of four probability uh, to be correct, and then you mix these two strategy, and if most of the questions you know how to do, then you can still get some very good score. So I think that's the idea. And I think next time I will explain the proof in more detail. So thank you very much.
Okay, thank you. Let me just check. Can you still hear me, Junyi? Junyi, can you still hear me?
Yes, I can hear you.
Okay. Let me just check with the audience now. Would anybody like to ask a question? I have one question while they're thinking about it. Back to the result about periodic points being Zariski dense. In the simple counter example you gave, the map didn't just fail to be cohomologically hyperbolic. It was also it fibered over a lower dimensional system. But there are examples, yes, of non-cohomologically hyperbolic maps that don't fiber. Do you have any expectation for those?
I think that I have some example, but the construction of this example is quite complicated, so I didn't write it down. So
an example that doesn't fiber.
Yes, I think I can at least I guess that I have some example because I didn't write it down. So it's an example in dimension two, which is in fact it's a family of example, and in this family, they are all rational self-map in dimension two, and they do not preserve any vibration.
I see.
And it is non-cohomologically hyperbolic, but some of them are, has Zariski dense orbit, and some of them are not Zariski dense orbit.
Okay. And the periodic points, they're not Zariski dense. Oh, some of the examples they're not Zariski dense.
Yes, some are Zariski dense and some are not Zariski dense. I think the idea is for example, I think the hard part is to construct some of it which has Zariski dense periodic point, and I think the idea is try to construct some map, and you compose it by some lift of Frobenius, and then you can show that if you do some specialization, because you have already composed some Frobenius, then it is attracting everywhere. So you get some attracting fixed point, and then if you back to this generic, then you can, because you have a lot of attracting fixed point. Attracting fixed point are isolated, so you can lift it to generic fiber. So you show that in the generic fiber you can still have a lot of periodic points. So I think the example is constructed like this, and in this construction there is no reason it preserves some vibration. But if you want to show that they actually do not preserve any vibration, I think this is quite, it's not so easy. So.
Yes. Are there any other questions? Oh, 1 second.
Thank you. Hi, Junyi. In theorem D, at the
theorem
end,
D. Okay.
Yeah. Assuming that you have a point X for which the Zariski closure of the orbit lies in some subvariety, would you expect a better bound on the upper arithmetic degree?
Let me see.
I think it's the
This
last.
theorem D.
Yeah.
Good question. So I think in this case, basically you need to generalize the definition of dynamical degree. So the dynamical degree is for this whole space, and you can still define it for some invariant subspace. But in fact, for every closed subspace, even it is not invariant, you can still try to define something very similar to the dynamical degree. It's something like you pull back this L sometimes and intersect and do some self-intersection and do the intersection with L and then intersect this subvariety to get a number, and you still get a sequence of some kind of dynamical degree. I think in the endomorphism case, you can see all these things are well defined. But in the rational self map, I am not so sure whether this number are well defined. But you can think it as some kind of dynamical degree for subvariety. And if you have this, I think you can still use this wandering dynamical degree to bound this arithmetic degree.
Thank you.
So it's also some control from some geometric set to some arithmetic set. So I didn't write down the proof, but my feeling is like this.
Okay, thank you. One last chance for questions. All right, well, let's thank the speaker again.
Thank you very much.
Thank you.